Thank you. Thank you for offering me to speak in this conference. If it's... Okay, thanks. So this conjecture is a problem, oops, going too fast, yeah, in the representation of reductive groups over local fields. But it has, its motivation are in the theory of L function, and particularly the interpretation of Langlands-Shady of L function. One of the founder of this area, the representation of reductive groups over local fields, Aryasomayajula, one of his goals was to achieve Plancherel theorem for local fields, so first complex and real groups, and in a second time for p-adic groups. So when you want to write this Plancherel theorem for any reductive groups, you need to define a Plancherel measure, which is given there, which is one of the expression of the Plancherel measure. And the measure, this is a measure on the dual of G, which is a set of unitary irreducible representation of G. And you see that there is a formal degree getting in this expression, and a mu function, so this mu function, which will be in one of the main ingredients in my work. So this mu function, the relationship with number theory is that Langlands-Shady managed to express it as a rational function, which is a ratio of L function and local epsilon factors. So the conjecture I will be talking about, which is related to this L function business, state that if you have a standard module, generic standard module, there is a unique generic irreducible subquotient, and this subquotient should appear as a subrepresentation. I will give you the statement after introducing all the notation. So going back to this Plancherel measure, which is one of the main interests in the theory, you have this first expression which I just gave you so that you have a different definition of it. So this is a Plancherel measure up there. And this one, which introduces the mu function, as I said, you have up to certain positive constants, this function, which will appear in my work. And you can express it, that's a relationship with number theory as a ratio of L function. So we have seen that last week, but I will remind you of some basics of representation of reductive groups over local fields. So first, you define this space of invariant function under, not completely, I mean, they are invariant up to this sigma m action on the group G, and you have a regular right action of this induced representation of this function. So this defines the space of induced representation of sigma nu, where nu is a parameter in this vector space. So you should think of this as a vector space, a real vector space. And when I write sigma nu, this is just a sigma tensor chi nu. So those parameter nu will be one of the main interests in my talk as well. One other object which is in the center of our work is a standard parabolic subgroup. So those parabolic subgroups are indexed by theta, where theta is a subset of delta. So you define a reductive group by a root system. That's a classical way to define a reductive group. This root system has a basis delta, and for any subset theta of delta, you can define a parabolic subgroup, which where the levy contains those roots in theta. In particular, you can compare standard parabolic subgroups because of some inclusion properties of this theta 1, for instance. One further result in this theory is Langlands classification, which is one of the main classification results. So assume you get a standard parabolic subgroup of a reductive group G, and you fix some tempered equivalence classes of tempered representation of the Levy M, and some parameter which is in the vector space, but more particularly in a Weyl chamber, and a positive Weyl chamber. So a Weyl chamber is just a cone in this real vector space, and you are choosing a parameter in this cone. And you consider this induced representation, which will be called the standard module. So when you have such a construction, you know there is a unique quotient, which is called the Langlands quotient, GP nu tau. And any representation, any irreducible, admissible representation of the group should be some Langlands quotient for some data of this sort. We have seen with Vincent last week the definition of cuspidal support. So this is just a reminder. In my context, I'm fixing some representation of sigma and not necessarily considering the orbit under the action of the group G. So we have this standard module, and now we can define an intertraining map between the induced, so this induced IP tau nu to the opposite parabolic. So this is the induced from the opposite parabolic. So let's say in GLN you have a B, which is a Borel, which is the upper triangular matrices. The opposite parabolic in this context, which is B bar, will just be the lower triangular matrices. When you have such intertraining map, it is defined as a convergent integral, where you integrate on this unipotent, the opposite unipotent radical. And this is convergent only if the parameter is far away from the walls of the Weyl chamber. And you see that the mu function I mentioned previously, which enter in this definition of the Planck measure, appear again here when you compose these two intertraining map. This is up to this constant. So the mu function, which we have seen, can be defined in different way. So in this definition of intertraining map, in the definition of the Planck measure we saw on the first slides, and you know as well that there is some relationship of this mu function with some L function. So one example for what I said about L function in the context of GLN. You fix so F is the local field, where Q is the order of the residual field, and you fix some discrete series of this maximal parabolic, M1 times M2. So because it is a maximal parabolic, you are thinking that there is one root alpha, which is outside of the root in M, in this maximal parabolic. So in this context, Scheidi introduced this notation alpha tilde. So S alpha tilde is this element in a positive Weyl chamber, AM, in this context, if M is M1 times M2. And this is just a discrete series of this maximal Levy. So up to this constant, which is given by this ratio of epsilon factors and some gamma factors, this is just a ratio of L function. So you have certain property of this mu function. In particular, so here I'm fixing some square integrable representation omega, and this is in the work. This is in the work of Valspurger on Harish-Chandra Planck theorem. If you look at different properties for this mu function, it has to be positive as part of this measure. So up to positive constants, the Planck measure is the mu function, so it has to be positive. And what is important is this second line, which is a factorization of the mu function. So you can factorize with each of these roots. So those roots are the roots of the root system. Let's say sigma is the root system of the group G. You can look at the reduction of these roots to a maximal split torus in the center of M, which is this AM. So you have fixed M, you have a maximal split torus in the center of M, which is AM, and you can restrict all the roots in G to this split torus. And then you define this M alpha as a kernel of alpha, or say if alpha is a simple root, you can think of delta, the roots in M alpha are just the roots which are in M, where you add this root alpha. So M is a maximal levy in M alpha. So I will use this formula later on. You get one more property of this mu function. It is invariant by the action of the Y group, as you see on this formula. And one example here with GLN. As you see, like those factors correspond to this mu M alpha, where if you look at two consecutive blocks, GLNI plus 1, when you add the root which connect them in some way, you get this GLNI plus 1. And you do that for all possible dual, not consecutive, but all components in this levy. You can do this decomposition. One last definition, one last way to see this mu function. It's in the context of a Cuspidor representation sigma of levy M, unitary irreducible. So what I mean by in a certain context is that you need this mu M alpha to cancel on sigma for each alpha. So if you get this condition, then you can write this mu function as this polynomial, depending on this lambda, which is the parameter here you have complexified the picture, but this lambda, we will look at the real part of it. So we'll look at this element in AM. So it is a function of this parameter. And as you see, there are certain zeros and certain poles. So the zeros up here, the zero of this function are when you get this scalar product, which root alpha equals 0. And if this scalar product is equal to plus or minus 1 or plus or minus 2, which are this value, you get a pole of this mu function. Also, we saw last week how important was the notion of generic representation in the talk of Amaya Pital. So he said that they are great. That's true. We use many theorems in the theory of automorphic form are proven for generic representation. So that's why I will care about generic representation. You know as well that there is, for classical groups, there is, in each L packet, there is at least one of them, one generic representation. There are many other results of this sort. What we have, when there is a generic standard module, what we know is that, so it's a generic standard module. What we know is that there is a unique generic subquotient, and this unicity will enter in the proof. So now you can understand the statement. You have all the definition to make sense of it. So I will consider a quasi-split connected group over a p-adic field of characteristic 0. And I assume I just, for the moment, I will just consider the root system of type ABCD, or you can take a product of such group as well. So let's pi0 be the unique irreducible generic subquotient, then it has to be a subrepresentation in the standard module. More precisely, that's a statement I actually prove. So I define a root system which is sigma sigma. I will give you a proper definition later. And in this context, so if sigma sigma is of type ABCD, you can show that this conjecture is true. And I have shown that if sigma sigma has component of if G is of type ABCD, then you know that sigma sigma will have a component of type ABCD as well. I don't. Do you see? Can you see what is written, or maybe it's a bit difficult for people on the last row? Sorry. So this is a kind of the architecture of the proof. So pi0 again is the notation for this unique irreducible subquotient in the standard module. So those are the ingredients, I would say, like the different steps to prove this central part. So this central part, first I will only consider the case of sigma irreducible. Tau is a discrete series, and P will be a maximal parabolic subgroup. And I restrict myself to the case where this unique generic piece is a discrete series. And from this central block, you can deduce the case of here non-discrete series subquotients, the context of a non-discrete generic irreducible piece. And from that, so this you need as well another sort of classification of parameters. This Langlands parameter I have mentioned in the definition of the Langlands classification. You can order them in a certain way, and you need that to prove the case of tempered and non-tempered subquotients. And from that, you can deduce a case of non-maximal parabolic and so on. So I will focus on the case of a discrete. So I will focus on the central block there, and I need to give you a definition to set the problem in this context. So let's first define the cuspidal support of a generic discrete series. There is a notion of residual point developed by Eiermann, and earlier actually by Silberger. He calls that Casselman point, but it's an equivalent definition. So you fix a cuspidal representation and irreducible unitary, and you will look at this nu, and if this nu if the number of poles minus twice the number of 0 for the mu function for this particular nu is equal to the dimension, this dimension. So let us assume G is semi-simple. You are just looking at the dimension of AL, which is equal to the cardinal of delta minus theta. If theta is so let me be more precise here. Let's say that this is L theta. So theta are the root in L. Basically, you are just looking at this cardinal. So this dimension in this context is equal to this cardinal. So you want this number of poles minus twice the number of 0 to be equal to this. And if you have such a residual point, this is the content of the next theorem. If this is a residual point for the function mu g, then this unjust representation has a discrete series subquotient. So you have a way to characterize this, like the occurrence of a discrete series subquotient by this condition of having a residual point. So that's another theorem which is much more specific. You look at generic irreducible representation, which are discrete series, not only discrete series, they have to be generic. Then there is a standard parabolic subgroup and some unitary cuspidal representation, such that you can embed this generic discrete series in this unjust representation. So here, being in the closure of a positive Y chamber is equivalent. I will talk about dominant parameter. So this is like the definition of dominance. You need to be positive for all the roots which are not in M1. And of course, you will be 0 for all the roots which are in M1. So now I want to describe the cuspidal support of this generic discrete series. So S alpha, so I'm in the context, I am in the context of M maximal. So I have this S alpha, which is the parameter of the standard module. And using this previous theorem of Eiermann-Obdam, you can you know there exists some standard parabolic subgroups such that you can embed this discrete series representation. So I recall that discrete series is this one, in the one in the standard module. You can embed it in such representation where this is in a positive closed Weyl chamber. And doing induction in stage, you have this quotient here. Pi 0 is a subquotient in this, the generic subquotient in the standard module. You can define the cuspidal support where this lambda is just nu plus S alpha. So now we have this alpha. So I'm going to focus on actually on this and just representation on the cuspidal support. And I want to describe more precisely this parameter lambda, which for the moment I just know that it is in this Lie this vector space AM1 star. So let's. These are the 3 steps to the proof, I would say. You first describe this cuspidal support, and we will use weighting Dink diagram. So this is related to the work of Obdam in the affine Ecke algebra context, where he has introduced the connection between residual points and weighting Dink diagram. In a second step, you embed, so that's part, that was the blue part in here. You need some kind of embedding of your generic subquotient in a particular induced representation with certain parameters. And once you have this embedding, you can just use a standard intertwining operator to be able to conclude. So let me define a weighting Dink diagram. So you all know what is a Dink diagram. So weighting Dink diagram is just that you will put some weight there under each root. Because those weighting Dink diagram in the context I use them, they correspond to distinguished nilpotent orbits. I only have weight 2 and 0. And there is a certain, those have been defined and completely classified by Bala-Carter. And you get some very strict condition on the number of consecutive 0 and 2 that appear in this weighting Dink diagram. As I said, we have a bijective correspondence between dominant residual points and some weighting Dink diagram that was initiated by Obdam in the context of affine Ecke algebra and introduced by Eiermann for p-adic reductive groups. So we have this correspondence, but what kind of root system shall we use? We are using this sigma I mentioned earlier, which are these roots seen as root of the maximal split torus in the center of them, such that the mu function has a 0 at alpha. So Silberger first proved that this is a root system and its Y group is denoted W sigma. And I will assume, as I said, that sigma is irreducible in the first time and of type A, B, C, or D. Then to get this, to get a description of the residual point lambda, I will actually need to get into account some reducibility results of this kind of induced representation. So I won't get into the detail here, but basically to know what kind of weighting diagram you need to use to describe the parameter lambda, you need to know what are the components of this sigma in case it is not irreducible, and some reducibility point for such an induced representation. And they are, because we are in a generic context, these reducibility points are 0, 1/2, or 1. And one last remark is that there is a unique, if you look at the Y group orbit of a parameter, a dominant residual point, or any residual point, there is only one dominant parameter in this orbit. So how to make this bijective correspondence work? Say you start with a weighting Dink diagram, and I want to describe the coordinate of residual point nu. So those are given actually by this product of nu with the roots of the Dink diagram. I have said that those are either 0 or 1. So like the weight where 2 or 0, and if it is 2, this scalar product is 1, 0 otherwise. So with an example of this root EI minus EI plus 1, if you compute this scalar product, you will get some, there is an increase by 1 going from the E coordinate to the E plus 1, the I coordinate to the I plus 1. And these two coordinates will be equal if there is a 0 under the root alpha I. So an example with this weighted Dink diagram. Here you start at this end, so there is a 0 on the last root, and it is a type B15, so you know that the last root is expressed as E15. This gives you that the last coordinate of the residual point is 0. And here, here on this one you have a 0 as well. So again, new 14 is equal to new 15 equal to 0. And the first increase by 1 is on this, this coordinate with a 2 there. There you will get new 13 equal to 1 and so on. So this is all you can compute in the basis of the vector space AM star or AM1 star. You can, which is given by this EI. You can compute the coordinate of this dominant residual point. So here I don't put commas, but these should have commas. So this is one type of residual point. I mean, the expression of this residual point in the basis of the vector space. And I will call such a sequence of integers or half integers residual segments when they are given by this weighted Dink diagram. As I said, those weighted Dink diagrams have been classified, so there is a lot of constraint on them. This is given by Bala-Carter classification. And because you have so much constraint on these P, there is a relationship between these Pi there. You get a relationship between the multiplicities in these segments. So each integer occurs with a certain multiplicity, and NL is related to NL plus 1 in general. So this is a technical definition. It's just to give you an idea of the constraints that appear for this sequence of integers that characterize the residual segments. So in the case of type A, so say I have a weighted Dink diagram of type A, it's only a sequence of 2. So type A, it's a very easy weighted Dink diagram are just given by 2 everywhere. This means if you understood what I said on the previous slide, that you have an increase by 1 on each coordinate. Sorry, I didn't know. I forgot I had written it there. So there you have a sequence, you obtain a sequence of decreasing sequence of integers. And if you know the theory of Bernstein-Zelinsky for the classification of representation of GLN over p-adic fields, such sequence remind you of the notion of segments as developed by Bernstein-Zelinsky. So this is why I call those construction residual segments. They correspond, as I said, like each dominant residual point, which is written as a residual segments, give you, by the theorem of Eiermann and Eiermann-Obdam, this give you a generic discrete series as a subquotient. And in the context of Bernstein-Zelinsky, you know that if you look at such induced representation with a dominant here, a segment, which is actually, in my language, a residual segment which is dominant, you have a unique quotient which is essentially square integrable, which is called the Steinberg representation. So the Steinberg representation is a sub-representation when you write the segments as in decreasing order like this one. And as I said, this is a general phenomenon. So in general, by the theorem of Eiermann, you can associate to a dominant residual point, written as a residual segment. You can associate a generic discrete series as a sub-representation. Okay. Yeah, so that's the example of the Steinberg. And as I said, as you know, the Steinberg is generic, so it is an example of this generic discrete series that occur when you get a residual segment. So as I said, I will just talk, I think I just have the time in this lecture to talk about the proof of the central block there using these ingredients. So that's the statement. I will fix tau as a discrete series of a maximal standard parabolic. And I just look at the generic discrete series subquotient case. So I assume that this generic piece is discrete series. So I want to describe this parameter lambda. So first, using Eiermann-Obdam, I will embed this generic piece in this induced representation where this is a dominant point for M prime. Then you use the Bernstein-Ziewiski theorem. You know that if there is one quotient in common in this induced representation from this cuspidor and in the same with P prime sigma prime, there is the same, they share one quotient, then they share all, I mean, their Jordan-Holder composition theory are equivalent. So all their quotients are the same. I have shown similar results in the context of having dominant parameters. So I am assuming that I have two induced representations from Cuspidor with two different parabolics. And I'm choosing, they share one common subquotient, and I'm choosing those parameters to be dominant. So one is dominant for P1 and the second one for P prime. And I show that there is an isomorphism actually between these two induced representations. So let's now consider the W sigma orbit of the cuspidal support of this generic piece. I will call W sigma the dominant. We know there is a unique dominant point, so this is the notation for the dominant point. And by the above proposition, there is an isomorphism between this induced representation and the one I first embed my quotient, my generic subquotient in. And now I know that I can describe this one using the Weytin-Dink diagram. I am in the orbit of the sigma lambda, and I am dominant, so I can use this Weytin-Dink diagram description. Secondly, because I have chosen alpha, I mean alpha is a root which is not in delta to define this subset theta. So I know that sigma m will decompose into two pieces. And it is true as well that sigma m will decompose into two parts. So this point, this new, which was in the construction at the beginning, it will be formed by one linear segment, so one of type A and one of type B, C, or D. So say in the case of classical groups, you have such a levy. So this is GL A minus B plus 1 times, say, a group, classical group SOP. So my discrete series tau is a Steinberg and pi, which by the theorem of Eiermann-Obdam should embed in this induced representation where MC is just SOP. Here you have a dominant residual point corresponding to this generic discrete series. And you know that the Steinberg also embed in the GL part, which is, and you know that there is this segment given by the definition of the Steinberg. So in this context, the lambda, the parameter, we have this sigma lambda we need to describe. this new lambda equal nu plus S alpha is just the gluing, if you want, of this linear segment AB and this N underline, which is a residual segment of type A, B, C, or G. So in this context, it's type C, actually. So let me get into an example so that you get a feeling of what's going on with these segments. So I will start with B7, and this Dink diagram gives you this type of residual segments. Let's say that G is SP24, and the dual group is SO25. So usually these residual segments, the parameter is in the dual of the Lie algebra. It's not in the Lie algebra. That's why here you have the dual group. And here, so this group, its type is B12. And in this context of principal series, you know that sigma sigma is actually equal to sigma. So in this context, sigma sigma is just B12. So I choose another weighting Dink diagram, which is this one, and which has this residual segment. So you can compute again by what I explained earlier. You can compute with the weights this residual segment here, and by the result of Heyermann-Obdam, you can embed this generic discrete series in this induced representation. So this notation just means you have this sequence of character, this tensored, this is tensored everywhere, right? And let me choose a standard module, which has this Cuspidor support. This is a standard module. I will get a Steinberg twisted by 2. And this B7 I define up there. So this is a complete, this is just an example I constructed, right? It's just to give you an idea of the question we try to answer. So this is B7, and this is the segments corresponding to the Steinberg twisted by 2. So now the question is, does pi 0 embed in this induced representation? So I will need to use standard intertwining operators to solve this question. So for the moment, I just have this embedding, but I want to embed in this Cuspidor support. And I need to use intertwining operator to do so. This is a classical result of Harish-Chandra. In this talk, I will use particularly the first point. So if you are a root in sigma sigma, so sigma p1 are just the positive roots. They are the roots in sigma am1, which are positive for the parabolic p1. So suppose you are a root there, but you satisfy this condition, so that means you are in sigma sigma. You know there exist some elements in the while group. So this is these elements in the while group which fixes m1. Such that this, you know, there exists such elements, and it fixes the representation sigma. The second part of the theorem won't be used in this talk. And again, like the mu function we are looking at, which is defined in this theorem, is this factor. So I want to have more precisely non-generic kernels intertwining operators. And I will explain you in the next slide how to use Harish-Chandra to understand this intertwining map. So let's say we have two parabolic subgroups having the same Levy subgroup M1, and you look at two induced representation where you fix lambda. This lambda here has to be dominant for P1, but anti-dominant for Q, which means in the negative while chamber, closure of the negative while chamber. I show then that there exists an intertwining map from this IQ to this one. And this map has non-generic kernel. I will need to use a non-generic kernel intertwining map to be able to conclude on the proof. So I need to use for this this proposition, I need to use the theorem, the module standard theorem from Heyermann and which tell you that if the Langlands quotient is generic, then it is just equal to the standard module. So let me explain how we use Harish-Chandra here to understand these some intertraining map with non-generic kernels. I choose this root alpha in sigma sigma, and I will look at the S alpha, the simple symmetry associated to alpha. So it acts on this parameter lambda. Because it depends only on two coordinates, it will actually act as a transposition on the I and I plus 1 coordinates. So you start with this map, which appear in the Harish-Chandra context. So you start from this map and you go to the opposite parabolic. So by the theorem of Harish-Chandra, you know that this map, you are there. So you have this S alpha which fixes sigma. This is actually, so this is the second map is the one of Harish-Chandra. Sorry. So this first map, I use this proposition because this parameter is anti-dominant for P1 in the context of A smaller than B. So assume that A is smaller than B. This product is strictly negative. So this is an anti-dominant parameter for P1. And it goes to P1 bar, so it will be dominant there on P1 bar. So this operator has non-generic kernel by the previous proposition. And the second operator is the one which is given by the action of S alpha, so in the Harish-Chandra theorem. And here you apply S alpha to this P1, so sigma is fixed. And S alpha applied to lambda is just a transposition. So you just use the classical definition of S alpha. S alpha is applied to some elements. It's just this, right? So if you apply this to this coordinates, you just switch, you just permute the coordinates I and I plus 1. In the end, the composition of these two operators give you, so you have just changed those two coordinates, you have permuted them in the context where you started from A inferior to B, and this has non-generic kernel, this map. You can do the same thing with a sign change on the end of your parameter. The last coordinate, you can change the sign. So this corresponds to the plus or minus 1 element in the Y group in the context of type B and C group, for instance. And then the action of S alpha is just changing the sign if you go from negative to positive, and this has non-generic kernel. So, to explain you now the embeddings, like these embeddings I need to be able to conclude. I need to look again at this orbit, these W sigma orbits, and you want some linear part and some residual segments of type B, C, or G, such that this one is of type B. In this context, we have fixed the White-Dink diagram to be of type B. And you want also rank 1, some intertraining operators with non-generic kernels going from this induced representation to this one, which was the one containing the standard module, right? This one. So we want some other Cuspidor support I can embed in, and then some map from this one to this one. So to define this, to get an example of such a pair, one has to define the notion of jumps. In the context of classical groups, Mogla and Pippich define Jordan blocks and Jordan blocks elements. So if you get a partition of 25 into disjoint odd integers, you can write each integers as 2 AI plus 1. So this is just the example. And here the jumps, I will define the jumps to be the 4, the 3, the 2, and the 1. Then I give you the solution of this game. This element, this pair we are looking for, is just this one. You get the linear segment with 2 jumps, 1, 4, and 1, -3. So you get the second jump with a minus sign. And this is some residual segments for type B4. So in my work, I have generalized this result of Colette-Mauglin on classical groups. So this is a very technical result. You want to embed this generic discrete series. In our context, it's even only a discrete series. If you know that this discrete series embeds in such an unjust representation, where this is the square integrable representation of the linear group with these segments starting there and ending there. Suppose you have such an embedding. You know there exists a discrete series pi0 prime, which appear here, so that you can actually embed in this unjust representation. So what is the difference? Here you go from a positive integers. Those are 2 positive integers. And A is jumps. No, A in this context is a Jordan blocks. But this is a Jordan blocks element, and this is a consecutive Jordan blocks element. Here you have changed the sign, and this is what we will need to get here this negative sign. So this is a generalization. I generalize this result of Mauglin, and from that you can get an embedding of, suppose you have pi0 embedding in this n pi0, which is a dominant residual point, residual segment. You know there exists some standard parabolic such that this generic, essentially square integrable representation of the Levy Mi with this cuspidal support. So here you go from jump AI to minus AI plus 1. You have ordered the jumps in a decreasing order, like this. Then you can embed pi0 in this unjust representation, and you know that the cuspidal support will be this one. So in the end, you will be able to embed pi0 in this cuspidal support through this embedding result. So now you got these embedding results, is the first line, and you want a composition of what I call rank 1, this operator I have been explaining you before. You can compose those rank 1 intertwining operator with non-generic kernels from this unjust representation to the one defined in the setting. Do you understand how to do that from the properties of entertaining operator I explained or not? How can I go from this sequence to this one by transposition and sign change, which have non-generic kernels? So I will start with -3 there, and -3 is smaller than 2. I have this condition of B smaller than A. And then I know that I can switch the 2, I can transpose the 2, and this operator has non-generic kernel. So this -3 can just move on the right, but it is also bigger than 1, so it can actually go all the way there at the end. So you have this -3 at the end, and here I explained that you can change the sign. On the last coordinates, this operation will have non-generic kernel as well. You will have an intertwining map which goes from -A to A with non-generic kernel. So on this coordinate, I can go there, change sign, come to 3, and because 3 is bigger than 0, I can go all the way up to there, to actually, no, I need to stop before the 0. So actually I go up there. And I will do the same with -1 and -2. I go all the way down, I change the sign, and I come back. So eventually you can go to this cuspidal support with this kind of operation. And again, these intertwining map have non-generic kernel. So in the end, this pi0 can just appear in this induced representation. And this induced representation contains the standard module. So by multiplicity 1, you know there is a unique generic piece. You can conclude that this pi0 has to appear as a sub-representation here in this induced module, this standard module. I think I'll stop there.